All right, so this is our first chapter for BSC 2010C. It's chapter 2. Due to time constraint, we had to skip chapter 1. It's chemical context of life. But before we can dive into that, we first have to identify what characteristics you have to have in order to be considered a living thing. There are 8 of them. Whenever my students and I have sat down and tried to list them all out, there's always one that gets forgotten. So we've learned to just sit down and write them in alphabetical order. When you do that, you tend to always remember what they are. So C, D, marker's not dying on us, so let's switch it out. C, D, E, G, H, M, R, R. Check. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So they have to be made of cells. The organism has to be made of cells, has to contain DNA, has to be able to evolve, it has to be able to grow and develop, has to be able to maintain homeostasis, big fancy schmancy word. Let's break it down. Simple meaning, homeo, just like homo, same. Stasis, status, so keeping everything constant. So constant temperature, constant pH, everything has to stay the same, all right? Metabolism, it has to reproduce, and finally it has to respond to the environment. Okay, now, I could take a rock. A rock can sit here, it could fall to the ground, it could form little baby rocks. That would be production. I could take a rock. I could put it outside in the sun. It would get warm. That would be responding to environment. I could take the same rock. I could put it in a freezer. It would get cold. That would again be responding to environment. I could take a jagged rock. I could put it in a river. That jagged rock would eventually smooth out. That would be a form of evolving. I could have a rock. Under the right circumstances, grow with beautiful crystals in the middle of it. That would be grow and develop. I could argue that the rock could actually have forms of iron in it that when exposed to oxygen would turn into rust, which are obviously reactions. Metabolism is all the reactions put in together. Sorry there for a second. So we could technically argue in some weird way that that would be a form of metabolism. Very weird way, but we could argue it. So we could say that a rock is a living thing because it has 5 of the 8 characteristics of living things. But is a rock a living thing? Obviously it's not, because it does not contain all 8. So in order to be considered a living thing, you have to have all 8 characteristics. Viruses, for example, big debate right now in the scientific community that viruses are not a living thing by the scientific standards. Some say it should be, but as of right now they are not. So you have to have all 8 characteristics. So I want you to keep this in mind as we go through all of these chapters. So chemical context of life. When I was a biology student, I never understood why the second chapter of every biology book always dealt with chemistry. If you understand the importance of chemistry, it'll really help you understand the upcoming chapters that we have. And it'll make life so much easier. And it really does have a huge important role to it. So, first thing we got to make sure that we remember is that, number 1, what is matter? In order to have matter, it's anything that's going to take up space and has a mass. Basically, every organism. The matter is not specific to just living things. That same rock we talked about takes up space and has mass. So, it has matter. Alright? So it's not just specific to living things. An element, a substance that cannot be broken down to any other substance by chemical reactions. What's really kind of crazy is back in the day, scientists, when they started finding these elements, they knew that things were going to be filled in. They didn't know what yet. They hadn't discovered all of the elements, but they knew certain things were going to fill in over time. So they left these gaps. And little by little over time, we discovered all of these things. We have 118 of them now. And they filled in the entire periodic table. Took a little while, but we got there. So, of those 118 elements, we have 92 that are natural elements. When you take 2 or more elements and you put them together, you form what's called a compound. substance consisting of 2 or more different elements. This right here, anybody guess what this is? You've got 2 of the same atoms, the same element. Those are hydrogens. And this right here is 1 atom of an oxygen. So that's H2O. Whenever you see me draw H2O, I will not be drawing it this way. This is the correct way of drawing it, but it is not a very fun way of drawing it. When I like to draw water molecules, I will draw them Mickey Mouse ears. It'll be Mickey Mouse face turned upside down. This right here turned. It's just a little more fun. Chemistry teachers hate it, but I like it. So I tend to turn it, make things a little less intimidating. You've got your NaCl, that's your salt, table salt. Anybody know what this might be, by chance? If you don't, it's not a problem at all. Just wondering if anybody might be able to take a wild guess at what this might be. This, in fact, is C6. We have 6 carbons, H12, 12 hydrogens, O6, 6 oxygens, and that is your glucose. So we'll be talking about that more as we come up in the upcoming chapters. Your 4 most important elements of the 92. There's 24, there's 25 that are essential to life, but the 4 that are found that really make up 96% of living matter are CHON. Students have come up with that little way to remember it. CHON: carbon, hydrogen, oxygen, and nitrogen. Those are the 4. If you look in the textbook on page 32, table 2.1, you don't have to have that memorized, don't worry about it, but just kind of breaks it down a little bit better. And if you have issues with the book, with getting a hold of the textbook, don't worry about it. Let me know through Remind, and I can send you a picture of it. You can see it, not a problem at all. You can see the full breakdown, but those are really the 4 most important: carbon, hydrogen, oxygen, nitrogen. And you're going to have some that we need in very, very small quantities. Those are what we call trace elements. These are elements that are required in very, very small, minute quantities, like your iron, your iodine. Our red blood cells, that's not a hole, that's just an indentation. Your red blood cells do what in your blood? Hopefully, we said they carry our oxygen. And if you didn't, that's okay, don't worry about it. But they carry your oxygen. Oxygen, which has a positive 2 charge. Sorry, negative 2 charge. Well, why in the world does this red blood cell carry that oxygen charge? Well, the way it's able to do that is because your red blood cells has to have that iron right there. Because your iron has a positive charge, and what do we say about opposites? They attract. So that iron bonds to your oxygen, carrying your oxygen throughout your blood. So if you've ever known anybody to be anemic, you yourself, if you tend to stand up a little too fast and you might get a little lightheaded, if you tend to find a need to chew ice, or if you might crave steaks or hamburgers at a certain time, especially ladies, chances are you might be anemic. The reason I specified ladies is because after having your menstrual cycle and you lose a lot of blood, in that blood that you're losing a lot of iron. So you need to have an intake of iron to compensate for that, so that you have your red blood cells able to carry your oxygen. Otherwise, you can have all the oxygen in the world you want, without that iron, your red blood cells won't be able to carry the oxygen properly. This is a common problem for pregnant women. That's why in medieval times, we think a lot of women ended up dying in childbirth, is because they would actually have such low levels of iron that when they would, number 1, increase their blood volume to compensate for the carrying of the baby, that iron concentration would drop to 50%. Then they would give birth, have more blood loss, so more loss of iron, and they'd pass away because they wouldn't have enough oxygen to actually support their whole body functions. So iron level is very important, however, small quantities. Always want to make sure you don't get too much of it. If you're wondering what in the world these pictures are of, they're pictures of goiters. These goiters are due to low iodine concentration. Now, if you look at iodine, all you need is 0.15 milligrams of iodine. Iodine is something that's not very common in the diet of some of the poorer countries, some of the developing countries. So people who don't have iodine in their diet tend to develop these goiters, and all it takes is just a little bit of iodine intake and those goiters go away. Now, again, trace elements. So small quantities, not too much. You get too much, and it can be toxic. It can actually be deadly. So be careful. Now, atoms. Let's talk about these guys. What are the three things that make up an atom? First of all, what is an atom? Atom is the smallest unit of matter. So what makes up an atom? Hopefully we'll all remember it. Again, it's okay if you don't. Protons, neutrons, electrons. Now, what is where? In the center of your atom, you've got your protons and you've got your neutrons. Protons. Remember the charge of the protons. That would be a positive charge. Now, don't get tricked. Your neutrons have no charge. Think about this for a second. If your neutrons had the negative charge, then what was on the outside would have no charge. Well, then what would stop this right here on the outside from just flying away? You have to have the opposite charge of the proton on the outside, which would be a negative, because that, again, opposite attraction force is going to keep that electron, that's the electron right there, from flying off. So you have to have the positive and the neutral charge in the atom, in the nucleus of the atom specifically, and then the electron on the outer cloud. Make sense? Good. So, protons, neutrons, electrons. Your electrons are going to move at the speed of light. Okay? Think about this for a second. If you're moving at the speed of light, are you going to have a lot of mass? What's going to move faster, an elephant or a mouse? A mouse. So, you're going to have your electron moving at the speed of light. So this guy right here, he's not going to have a lot of mass. Okay? He's important. He has mass, but compared to this guy right here, he doesn't have a lot of mass. So it's so small, it's negligible mass. It's technically 1/2000th the mass of this guy. Any one of these, either one. So, we really don't worry about these guys when we look at the atomic mass. So for atomic mass, we're looking at the mass of the protons, number of protons, plus number of neutrons. That's it. Your atomic mass is your number of protons plus your number of neutrons. That's it. Your atomic number, that's who you are. That's your jersey number. You can't change your jersey number. If you change your jersey number, it's a wholly different ballgame, right? It's your personality. Your personality. Personality. So your atomic number is your number of protons. Okay? Atomic mass, protons and neutrons. Atomic number, number of protons. All right? Hopefully this is making sense. If not, do not hesitate to message me. This is just going over information. It's in white. You don't need to know. Anything that's in yellow is what I really need you to know. I just add extra information in case you want to make sure, just kind of have an overall review of this information from chemistry. But I am not going to test you on it. I do not expect you to know this for my quiz or for my test. But it's there for you if you want it. Okay? For our purposes, I gotta skip. Atomic number, again, that's your number of protons in the nucleus. It is unique to that element. If you change the number of protons, you are no longer that element. You become somebody else. You cannot change the number of protons and stay the same element. Okay? Atomic mass, number of protons, plus your number of neutrons. I got a couple of problems right here for you. So if you don't mind, we'll take a look at those real quick. So, see here? So for sodium, we've got an atomic mass of 23. Okay? The atomic number is 11. Remember, atomic mass is, what again? Protons plus neutrons. The atomic number equals your jersey number, who you are, your personality, your protons. So, I now know that my P equals 11. So basically, I am solving for N. So 23 equals 11 plus N. So I'm going to take 11 from both sides. 23 minus 11 equals 12. So I now know that this particular atom of 23 for sodium has 11 protons and 12 neutrons. Okay? Can you figure out how many electrons it has? Whoa, 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 whoa. Oh, you didn't tell us anything about the electrons. I didn't. But you know that protons are positive charge. Neutrons have no charge, and electrons have negative charge. You know the protons are 11, the neutrons are 12, and I did not tell you that this atom had a charge on it. So if I did not tell you this atom had a charge on it, that means it has 0 charge. That means this guy and this guy, your protons and your electrons, have to be equal to each other. So, how many electrons do you have? 11. Good? All right. I'm going to erase this because I want you to realize something about hydrogen. It's something that's going to come back in the upcoming chapter. I'm going to erase. You can always rewind and pause. Okay, for hydrogen. The atomic mass of hydrogen is 1. The atomic number of hydrogen is also 1. Again, what's the formula for atomic mass? Protons plus neutron. So, if my atomic number is 1, and that's my jersey number, my personality, who I am, that's P, that means 1 equals 1 plus N. That means how many neutrons do I have? I have 0. I have 1 proton, and again, I did not tell you it had a charge, so how many electrons am I going to have? 1. Good? Alright, so do more of these, and you will see questions like this on the quiz, so make sure you feel comfortable with this. Alright, I've told you, you cannot change the number of protons and stay the same element. No changing protons. I've told you, if I change the number of electrons, if I have a different number of electrons than protons, then I'm going to have a charge. Yes? If I have a charge, I don't know if you remember this from chemistry, and if you didn't have chemistry, don't worry about it. We're doing this whole chapter is basically a basic / review of chemistry, basic chemistry chapter. So don't worry about it. It's okay. All right? But if you do have a different number of protons and electrons, then you are what we call an ion. Okay? And how in the world do you remember that an ion is something with a charge? I've not come up with a way to remember that. I'm sorry. You just kind of learn it. Okay? I try to always come up with easy ways to remember things, but every once in a while, I don't have something. If you come up with something, send it to me. You'll get a sticker. Stickers are worth bonus points with me. So, let me know. We can't change the number of protons. We cannot change the number of electrons, because then we're an ion. So, if we're an isotope, what's the last thing we can change? Hopefully you're saying neutrons. That's the last thing we're talking about. So if you change the number of neutrons, then you're talking about an isotope. Okay? With an isotope, you change the number of neutrons, protons stay the same. One of the most important isotopes that we have, especially when we talk about fossils, is carbon-14. Carbon-12, which is what we find in 99% of our carbon, is your typical atomic mass of a 12. And then you have 2 other isotopes, carbon-13 and then carbon-14. Carbon-14 is one that's used for radioactive dating. So if we're to find a fossil and want to know how old it is, we look at carbon-14 to see what's going on. See how old it is, figure out. That's how the scientists are able to look at the fossil and say, hey, this fossil is 35 million years old. Okay? It's thanks to this little guy right here. Let's look at this. This number right down here, the bottom, That's your atomic number. Okay? That number up here, that is your atomic mass. So if you don't mind, I want to take a second with these three guys and figure out the number of protons, number of neutrons, number of electrons. Okay? So for carbon 12, my atomic number is 6, Jersey number, my personality, who I am. So how many protons do I have? I have 6. If I have 6 protons, how many electrons do I have? I have to have 6 because I don't have a charge right there. Okay, Falk, you keep talking about charge. What are you talking about? Okay, it's a good question. Plus 2, plus 3. Minus 2, minus 3. Anything like that. That would be a charge. That would be an ion. We don't have that. That tells us protons and electrons have to equal each other. By the way, shame on me, they're supposed to be lowercase. Let me change that real quick. So, protons, neutrons, and electrons. So, 6 and 6. Now, how many neutrons? Well, 12 minus 6 equals 6. My videographer behind you is giving me the answers. So, carbon 13. How many protons? My atomic number is 6. So it is again 6. Number of protons have to equal the number of electrons. So we have 6. Neutrons. This time it's 13 minus 6, which is 7. Very good. Carbon 14. How many protons? 6. Protons have to equal electrons. How many? 6. Neutrons is going to be 14 minus 6, which is 8. This all stayed the same. So did this. What changed? Neutrons. Therefore, this is an isotope. Good? All right. I am going too fast. Don't forget, I am here. It's 4 o'clock. My office hours are at 4 o'clock before night classes every night. So feel free to come in early. I'm always here after our night class, so feel free to stay late too. And always message me on Remind. You can always email me, but I promise you, Remind is the easier way to get hold of me. So, radioactive isotope, isotope in which the nucleus decays spontaneously, giving off particles and energy. Like we mentioned earlier, that's why we use carbon 14 to figure out what it is, and to date fossils. Okay, now let's go back over here and look at our atom. In the center of our atom is our nucleus, where we have our protons and our neutrons. On the outside, we have our electrons. So when two different atoms come in contact with each other, what is going to touch first? Hopefully you're saying electrons, right? So what subatomic particle is involved in bonding? It's your electrons, because that's what's going to bump into each other first, okay? Now, you've got energy. Obviously, energy is what we need for anything to occur. Then you have potential energy, the energy that matter possesses because of location or structure. All right. I have 2 college books, Marine Biology, College Bio. College Marine Biology, College Bio. Apologies. They're at the same height. I'm going to release them. Which one of the 2 has greater potential energy? If they're at the same height, height is no longer the factor. So what's the factor? It's going to be their weight, right? How are we going to be able to distinguish, which one is releasing the most amount of energy based on its sound, right? So we'll release the first one, we'll release the lighter one, the one that has less mass. Listen for the sound. Pretty decent. Okay. Now we'll release the second one. Ready? Oh, that was not a good one. We'll do that one again. Sorry. Let's try that again. Okay, I'm not doing well. Let's try this way. Third time the charm. Let's hope. 3, 2, 1. Much better. So, based on that, which one of the two had the greater potential energy? The heavier book, the college Bible book. Yeah, half of which we're covering in this semester. So, it's going to be this one, right? Because it's heavier. Now, same book, different height. This was the original height. This is the second height. I'm not releasing it. But, which one of the two heights is going to have the greater potential energy? The one higher up. Exactly. So, sometimes the same thing, different heights, different locations, is going to have different potential energy. Keep that in mind as we talk through electrons and different orbital levels and all that fun stuff. Now, more distant electrons are from the nucleus, the more potential energy they have. Periodic table. I'm not asking you to go buy a periodic table. I am going to strongly recommend that you have a periodic table tab on Google open whenever you're doing anything when it comes to looking anything for chapter 2, for your quiz. Have one available for you somewhere. If you can print one out and have it, that'd be awesome. For our test, I will have one for you. For when that's in class, I will have it for you. Because it's the best cheat sheet ever invented on the planet. And once you keep that in mind, then you start to look at that thing and go, ooh, I love you. So you just have to realize how to read it, okay? But yeah, the further away you are from the nucleus, so if you look right here, if you're on the first orbital level, you've got some energy. And you've got the second, and you've got the third, and you've got the fourth, and you've got the fifth, and you've got the sixth. Actually, there's a seventh, but I'm running out of room, so I'm not going to do it. But I'll squeeze it right here. There we go. Now, if you have an electron that drops from here all the way down to here, he is going to release a whole heck of a lot of energy. Versus an electron that is going from here to here. He's not going to release as much energy. So you want to keep this in mind. Okay? All right. Each period of the periodic table of elements represents the number of electron shells in the atom, and each group represents the number of electrons in the outer shell. Yeah, that's awesome, Falk. What does that mean? All right. We got to go to the periodic table. So, in chemistry, there's something called the octet rule. If you've had chemistry before, might be ringing a bell. If you haven't, you're wondering what I'm talking about. Don't worry about it. Let me throw these words at you. Octet, octopus, octagon. What do they all have in common? Hopefully you're thinking of the number 8, and that is 100% correct, okay? In order to be happy, an element has to have 8 electrons in an outermost shell. If you look at these different columns, we're going to ignore these guys in the middle for a second. Trust me. Right here, look at these guys. Believe it or not, based on their column, it tells us how many valence electrons, fancy schmancy way of saying the number of electrons they have in their outermost shell, they have. So if you're in group 1, you have 1 electron in your outermost shell, 1 valence electron. Whether you're hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, you have 1. If you're in group 2, you have 2. So if you have 2, how many more do you need to be happy? You need 6 more to reach the magic number of 8. You have 2, you want 8, so you're missing 6. because you're trying to get to the octet rule, the magic number of 8. So 2, you need 6 more to get to 8. If you have 1, you need how many more? You need 7. We're skipping these guys. We're skipping these guys. Trust me, biology, we're skipping these guys. We're going to jump to 13. Now, I don't want to make a mistake. We're really supposed to jump to 13. If you're in group 13, how many did you have? If you're saying 13, I can understand the misunderstanding. But remember, I said the magic number was 8, so it's not going to be anything higher than 8. So what's the answer? Hopefully you're saying 3. Because group 1 had 1, group 2 had 2, so then the next number is going to be 3. What do? Just cover up that 1. He's got 3. So if he's got 3, how many more does he need to get to 8? He needs 5 more. Good. Group 14 has 4. Group 15 has 5. 16 has 6. 17 has 7. 18 has 8. Oh, whoa, 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 whoa. Hang on. So group 18 already has the 8. So they're happy. They don't need any more. These are the guys we call the noble gases. They are not going to bond with anything because they don't need anything. They've got everything they need. So they're not going to bond with anything. They're just going to chill. They just float around in life. That's your neon. Yeah, like neon signs. Your argon, your krypton, your xenon, radon. Yeah, I saw a mistake. I skipped helium for a reason. There's 2 words I hate to say. Always and never. Because as soon as you start saying always and never, there is exceptions that are come at you. So, helium, if you look at this top row right here, there are only 2 elements on that top row. There's a reason for that. These 2 guys are the 2 exceptions to the octet rule. They only need 2 electrons in their outermost shell to be happy. Not 8. They only need 2. So helium only needs 2 to be happy. But because he's full, we've got him over here with the noble gases, even though he only needs 2. Okay? This row has 1 electron shell. This row has 2 electron shells. This one has 3, this one has 4, this one has 5, this one has 6, this one has 7. What in the world am I talking about? Those circles around the nucleus. That's what I'm talking about. And then however many electrons you draw on each one of those circles is represented by the column. If you're in column 13, you have 3 electrons in the outermost shell, you're missing 5. We good with that? Okay, back to the PowerPoint. And then a periodic table for you in case you need access to one. Various electrons in the outermost shell. Let's go back to that for a second. So, if you are sulfur right here is in group 16. So sulfur's in group 16. So he has how many valence electrons? He has 6, right? So if he has 6, how many more does he need? He needs 2 more. So which group is he going to bond with to get 2? He's going to bond with somebody in group 2, right? Let's look at chlorine for a second. Cl. This guy right here. Chlorine is in group 17. So how many valence electrons does it have? He's got 7. How many more does he need to get to 8? He needs 1 more. So who's he going to bond with to get to 1 more? He's going to bond with somebody in group 1. Oh, who do we see in group 1? Sodium. When you mix sodium and chlorine together, you get salt, right? Okay, 1 more, and then I'll hush. Oxygen. Oxygen's in group 16. So how many valence electrons does it have? He's got 6. How many more does he need to get to 8? He needs 2 more. How's he going to get 2 more? He's going to bond with who? Yep. He can bond with somebody in group 2. Is that the only way he's going to get to bond, to get to 8? What else could he do? Could he bond with group 1 twice? Yeah. Huh. Look at that. Here's your hydrogen. 6 plus 1 gives you 8. A hydrogen plus a hydrogen plus an oxygen gives you water. Well, look at that. When you understand the octet rule, and you understand it's all about getting to the magic number of 8, now you understand why everything is bonding together and what all those numbers represent. Okie dokie? Hopefully yes. All right, let's keep going. Advanced electrons. That capital E is not supposed to be energy. It is supposed to be a lowercase e for electrons. I apologize for that. The E with the negative next to it is electrons. All right? This is just showing you about the different sections of the periodic table. Don't need to worry about that for my sake. It's just reminding you that you're never going to get more than 2 electrons per orbit. Okay? You don't need to worry about this slide. I used to make a big deal to go through and teach electron configuration, something that you guys were really taught in chemistry. If you're going to be taking chemistry in college, stop by and see me before or after night class one day, and I will gladly teach you a super simple way of understanding this. But for time-saving purposes, I'm going to bypass it, okay? But please, 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 if you're going to take chemistry in college, come see me before you take it. Chemical bonds. All right. So again, bonds are made by the electrons, involving the electrons. Now, there's strong bonds and there's weak bonds. When it comes to which bonds are the strongest, after a very long, convoluted conversation between 2 other professors and multiple research, going through a bunch of different books, here's the end story. Which one's strongest between ionic and covalent? It all depends on the situation. So we just both call them strongest. Okay? Covalent ionic bonds are the strongest bonds. Here's how you remember it. Covalent, you are a couple, and if you're a couple, you have to share. So covalent bonds is where you are going to share electrons. Okay? But you're only going to share the valence electrons, the electrons in the outermost shell. Because your other electrons on the inner shells, they're full. So you're not going to mess with those. They already have that octet rule completed. Those don't get messed with. You're going to share those other valence electrons because you're trying to get to the magic number of 8. That's why you're making bonds. Again, noble gases will not do this because they're full. They will not do any of this. Covalent bonds, sharing of electrons. But those electrons may not be shared equally. If you have a covalent bond and you take 2 or more atoms together, you have now formed a molecule. Okay? If you talk about a molecule, you have to involve a covalent bond. This is a big deal. People will call a salt